Hello everyone. Hello everyone. In this video, we are going to study introduction about the electronics lab. That is the which is the third semester lab in the VTU syllabus, and the subject code is 18WL38. And this lab is being handling by Professor Amlia and Professor Deepika. Now we will move on to the electronics lab. Till this, you are going to study about the theoretical explanation or theoretical background about the electronics lab. So we know that this is very important lab because and the branch is also electrical and electronics. By using the electronics concept, that is the miniaturing circuit concept, we can actually build a good type of electrical circuit also. So therefore this lab is very important as from the syllabus point of view. So now we will move on to the experiments which related to the electronics lab. So actually we have cycle 1, that is we are going to classify the experiments, that is cycle 1, cycle 2, cycle 3 and cycle 4. So in the cycle 1 you'll be having 4 experiments. So that is experiment number 1, 2 and experiment number 6 and 7. So the experiment number 1 is that it is about the design and testing of full wave center type transformer and also a bridge type rectifier circuit with and without capacitive filter, and also determination of ripple factor regulation and their efficiency. And in the second part, in the second experiment, we are going to study about the simplification realization of Boolean expression using logic gates and also using the universal gates. And the third one is nothing but it is the realization of half of full adder and half of full subtractor using logic gates. And the fourth experiment is that studying frequency response of single stage BJT, FET, RC coupled amplifier, and determination of half power points and the bandwidth input and output impedances. So this is about the experiments. So now we will be studying one by one the experiments. Okay. So in this laboratory, these two instruments are very important because by using this only we can actually construct the analog related experiment, and for the digital based experiments we'll be having a different kit for that. We'll be calling it as the trainer kit. So that will be used for the digital type experiment and for the analog type of experiment. So these two are very important. And the upper one instrument will be called as the function generator, and the below one the instrument is called as the CRO. So in the function generator, so if I want to say about the function generator is one which is going to generate the signals or the which is going to generate actually the voltage signal with a different frequency and with the different pattern and with the different amplitude. Okay, so this can be obtained by using the function generator. So the function generator is nothing but what? The function generator is going to generate the voltage signal with a different pattern, that is with the different types of waveforms and with the different frequency and with the different amplitude. So this is actually the basic function of function generator. So the function generator consists of first one display screen. So this display screen is used to display the frequency which we have selected. Okay, so this is going to represent the frequency. And we have coarse and fine knob. So this coarse, whatever you can see, this is the coarse adjustment knob here, which is used to vary the frequency in terms of large difference. That is, for example, if you want to vary from 20 to 25 or 25 to 30, then we are going to use this type of adjustment. And for the fine adjustment with respect to the fractional or the decimal point adjustment. That is, if I want to keep the frequency as 25.5 or 25.6, like this, fractional adjustment can be accurately made by using this fine adjustment. And we have the frequency range button. So you can see here, so this is the frequency range. You can see here this range is varying from zero point 0.1 to 1 megahertz. So like this, from the smaller value of the frequency to the very big value of frequency, we can vary by using this control knobs. So you can see here, this is something like a push button. So you can see here, here actually the 10K push button is pressed. That means what, I'm going to vary, I can vary the frequency from 1K to a 10K. So therefore you'll be having this type of adjustment. And here also the large difference adjustment can be made by using coarse adjustment knob, and the fractional or decimal point adjustment can be done by using the fine adjustment knob. So this is with respect to the frequency range knobs. And we have duty cycle knob. So duty cycle knob is nothing but what, it is something like you are going to vary the on and off time of the uh, waveform, or you can actually vary the rising time and the falling time of the waveform. So that is nothing but the duty cycle. So that can be varied by using the duty cycle. And it is the invert button, you can see here. So this is the invert button. So this invert button is usually used for the inverting of the signal. And we have function button. So this function button can vary the function of the waveform. That means what, either you can obtain the sinusoidal or triangular or pulsating, or I can say it as square wave. So these three types of waves can be obtained by using the function button adjustment. And we have attenuation button. So this is usually used for the setting up the voltage level. And we have synchronous terminal. So this actually gives the triggering pulses. Usually in a power electronic devices, we will be using this triggering pulses for switching on and off of the device. So during that case, we will be using this terminal. And you can see here, so this is the terminal which is something like the output of the function generator. So this output can be connected to any circuit or CRO through a probe. So whatever the probes we are having, through these probes we can actually connect the output of the function generator either to CRO or to any circuit. So this is nothing but the CRO. So CRO is nothing but cathode ray oscilloscope. So the cathode ray oscilloscope is mainly used for displaying the signal or the waveform, and it is also used for the measurement of the voltage in the waveform, and it is also used for the analyzing of the waveform. So these three phenomena can be accurately obtained by using the CRO. So what I told you, CRO displays the signal or the waveform, and also we can actually measure the value of the signal or the voltage of that particular signal, and also we can analyze the signal. So this can be done by using the CRO display screen. So this is actually a CRO display screen. And actually whatever the axis you can see here, so this is the x-axis, and from this x-axis, this is nothing but the x-axis, or we call it as time axis. And by this we can actually measure the time of the, or the period or time of the signal, and this adjustment can be done by using this. So you can see here, so this is the time per division knob. By using this adjustment, you can have the variation of x-axis in the signal. And this is the y-axis. This is usually a voltage signal, and by this you can actually measure the voltage. That means what, here actually this, if I say if the sine wave is covering from this end to this end, so this is something like a 10 volts, 20 volts, 30 volts and 40 volts, like that the adjustment is there in the CRO screen. And we have different control knobs also here, and we'll be having two output from this, that is channel 1 and channel 2. These two channels can be connected to any part of the circuit. Like this, we have different adjustment knobs. So once we get into the demonstration of the experiment, I'll explain in detail what is actually the different controlling knobs are there in the CRO. So next, we will let into the testing, that is the experiment introduction. So first one is called testing of rectifier circuit. So you all know that rectifier is nothing but what? Which converts the AC waveform into the pulsating DC waveform. So this is nothing but the testing. This is nothing but the rectifier circuit. Usually we are going to build the rectifier circuit by using the semiconductor devices, something like the power electronic devices like GTO. From that GTO, FETs, MOSFETs, by that we actually build them. So we all know that diode is nothing but what? Diode is nothing but a semiconductor device, and it conducts the current in only one direction. So that is nothing but the diode. So here we are going to construct the rectifier circuit by using the diode. And the application of coming to the application of diode, mainly the diodes are using for the switching action, that is for owning and offing of the circuit. So that is actually the basic application of the diode. So in this experiment, the aim is something like this, that is the testing of the rectifier circuit. That means we are going to build, or we are going to rig up the circuit, and we are going to test whether the output is in the required form or not. So that we are going to study in this. And also we are going to determine the ripple factor regulation, and also the efficiency for two kinds of circuit, that is one thing for full wave center tap rectifier with and without filter, and also the full wave bridge rectifier with and without filter. So this is with respect to the aim. And define of the diode rectifier. Diode rectifier converts AC into the pulsating DC. So you can see here, if this is my input signal, that is the alternating signal, and the expected output is in this form, that is in the direct waveform, that is in the straight line we are going to expect the output. However, this ideal condition can't be reached. So therefore, usually the pulses will be present in the wave. So therefore, we call this is as a pulsating wave, and this is usually the variable wave. So this is nothing but the diode rectifier. So now we will be studying about the center tap full wave rectifier. So you can see here, so this is the circuit diagram. So usually we are going to construct, or we are going to build this rectifier, we are going to build the circuit either in the breadboard, or also we can build it in the springboard also. Okay, so what is springboard, breadboard? So that also I'll give you introduction in the other video. Okay, so now coming to this, so the apparatus required in this kind of circuit is that, so we require actually the step down transformer with the center tap in the secondary. So that is required. And also we need two diodes, and also we need a resistor of 100 ohm rating, and also we need the DRB box. So DRB represents, it is the decade resistance box. So I'll repeat it again. DRB means it is the decade resistance box. As I shown you in the function generator, we have the different frequency range. In the same way, in the decade resistance box, we have different resistance range. So therefore, you can have a different resistor. That is, instead of changing the resistors like resistor oftenly, we can actually use this DRB box. So therefore, if you vary the knobs in the DRB box, then you can actually obtain the particular value of the resistance. Okay, so these are the some of the instruments required, and also we need the CRO probe. And also we need CRO probes, and also the CRO instrument. So this is the step down transformer. So the step down transformer is used. Why? Because the input is 230 volts AC, and I don't want to, like, the rating of the diode is not up to 230 volts. It is usually in the range between 15 to 20 volts. So therefore we need to reduce the voltage. So therefore the step down transformer is used, and this is something like the center tap transformer, because in the secondary it is having the third terminal at the middle turn. Okay, so if I say if it is having 5 turn, and that is in the third turn, it will be having the center tap terminal. So therefore this is something like the center tap transformer. And the one end of the transformer is connected to the diode D1, that is to its anode, and from the cathode we are going to connect to the diode cathode, that is diode D2 cathode, and from the diode D2 anode we are going to connect to the other terminal of the transformer, and from the center tap we are going to connect to the resistor 100 ohm. Then in series with that we are going to connect to the DRB terminal, and from the other DRB terminal we are going to connect to this junction, that is cathode junction of the two diodes. So like this the connections are made. So now coming to the procedure, we have to switch on the supply. When you switch on the supply, we are going to see the output, that is the V naught in the CRO. That is, am I getting the correct output or not? Then actually we are going to measure the voltage, then we are going for the calculation part. So this is the sinusoidal wave from the input. So this is the sinusoidal wave we are having, and by this diode action we'll be obtaining this output. So coming to the working of this circuit, so what is actually the working of this circuit? During the positive half cycle, the diode D1 is forward bias and hence it conduct. Diode D2 is reverse bias and hence it does not conduct. So therefore, secondary current flows in this way, that is from transformer to diode D1, then to the DRB, then to resistor R, then to the transformer again. So therefore, this is rectified, and in the negative half cycle, what happened? Diode D2 is conducting, so therefore current will be flowing from D2, and again it also follows the same path. So therefore, you are going to get the negative half cycle in the positive part. Like this output is obtained. You can see here, so this is not exactly DC, it is only the unipolar signal, it is not bipolar signal. Yes, that is agreed, but it is not still DC. Why? Because it is having ripples or pulses in the waveform. So therefore, to remove this ripple or to remove this pulses, we are going to use the capacitor. The capacitor is acting as a filter, and this capacitor will remove the unwanted signal, something like the pulses in the circuit. So you can see here, if I connect the capacitor of 100 microfarad and the working remains same, so you can see here the output will be in this form. You can see here the output is in this form. Therefore, you are going to get even more better waveform than this type of transform, this type of thing. Okay, so this is nothing but the working of the center tap transformer. And coming to the procedure, rig up the circuit as shown in the circuit diagram and switch on the input supply and verify whether expected waveform matches the output waveform or not, and measure the maximum value of the output voltage, that is the V maximum we need to measure, that is the highest value of the waveform or the magnitude of the waveform we need to measure. By measuring that, we can actually go for the calculation, that is we can actually calculate ripple factor, efficiency and the load regulation, and we can actually tabulate the reading, and from that we can actually calculate VDC, VAC and VRMS, and also we can do the same procedure for the bridge rectifier also. So coming to the center tap transformer, for without filter, this is the VDC voltage, that is 2 Vm by pi, and this is the VRMS voltage. The formula is Vm by root 2. That means what? In this experiment, you have to measure only the Vm. Okay. So if you measure Vm, you can actually calculate all these parameters. That is VDC can be calculated, VRMS can be calculated, and VAC can also be calculated. That is square root of V square RMS minus V square DC. And coming to the ripple factor, it is VAC by VDC. So that means what? Ripple factor signifies how much actually the ripple is present in the signal. So that is nothing but the ripple factor. And coming to the efficiency, it is nothing but V square DC by V square RMS. So which that is output by input into 100. So this is nothing but the efficiency. And regulation is nothing but VNL minus, that is V no load minus V full load divided by V full load into 100. This is nothing but the regulation. So for any experiment or anything, efficiency should be maximum and regulation should be as less as possible. And coming to the width filter, the ripple factor formula is 1 by 4 root 3 F into RLC. You know that frequency is 50 Hertz. There is no difference in that because it is the means frequency, and the RL is nothing but the load frequency, that is the DRB box frequency. Okay, sorry, DRB box resistance. So what value of resistance you have used in the DRB box, so that is nothing but the RL, and C is nothing but the capacitance value. So that is usually the 100 microfarad. So if you know, like usually we are going to fix the ripple factor as 2.5%. If my ripple factor is 2.5% and capacitance is 100 microfarad, that is for this design. If I want to for this value, if I want to design the circuit, then usually the RL will be in the range of 1154 ohm. So that can be actually calculated, that can be actually kept in the DRD box. And here actually the VAC is nothing but we are peak to peak value. So here it is only the peak to peak value. It is not the amplitude or the maximum value. It is only the peak to peak value. So that is nothing but the VRPP. So I'll tell you in detail when I conduct the experiment. Okay. So this is with respect to the width filter. And coming to the tabular column, so here we have for center tapped and for also the bridge wave rectifier. So I'll explain the bridge wave rectifier in the further slides. So here VM has to be measured by using the CRO screen, and VRMS can be VRMS, VDC, and all these things can be calculated by using the formulas. Okay, so this is nothing but the tabular column without filter. So for with filter, as I told you, the formula is little different from that. So again, here also we need to measure the peak to peak voltage, and the other things can be calculated by using the formula, and those can be tabulated over here. So then coming to the bridge wave rectifier. So why we call it as bridge wave rectifier? Because the 4 diodes are connected in the bridge manner. So therefore this is the bridge wave rectifier. And again here also we are going to use the step down transformer. So the one end of the step down, usually first what we will do is, so we will build this diode circuit in this manner, that is cathode to cathode. Like this we are going to construct in the springboard or in the breadboard, and across it we are going to connect the 100 ohm resistor, that is the power resistor, and also the DRB box, and output will be measured over here. And one end of the transformer is connected to this leg, and the other end of the transformer is connected to this leg or this arm. Okay, so like this the connections are made. And coming to the working, so in the positive half cycle, D1 and D4 are forward bias. So therefore these two will conduct, and the current will be flowing from transformer to D1 and to these resistors, that is to the load, and to the D4 and back to the transformer. And in the negative half cycle, D3 and D2 is going to conduct. So therefore current will be flowing, current will be flowing from here, that is from transformer to D3, that is to D3 to the load and the resistor, and to the D2 and to the transformer again. So like this the circuit is going to connect, and therefore you are going to get the output voltage in this form. And if you use the filter, the output waveform is smoothened, and you are going to get more and more good waveform with respect to the DC. So this is nothing but the bridge wave rectifier. So next, coming to the formulas or calculation with respect to the bridge type rectifier. Again, for without filter, the formulas, all things are remain same. That is for ripple factor, efficiency, and regulation. Formulas are remain same. And here also for with filter also the formulas remain same. Okay, so here the thing is that you have to calculate the peak to peak value in the with the filter. Okay, so this is nothing but the bridge type rectifier. So this completes one experiment in the cycle 1, and in the next video I'll be showing how to conduct the bridge wave rectifier. So coming to the result, so whatever the observations we have made here, rather than writing in the wordings, we can actually tabulate our results. So that will be very helpful in comparing the things. So therefore, the performance, all the rectifiers are evaluated and tabulated as shown in figure. So this is for center tapped and for the bridge type. What about the ripple factor, percentage efficiency, and percentage regulation? So once you conduct, you'll get to know actually compared to the center tapped rectifier, bridge type rectifier is most preferred, because the efficiency is improved over here, and the regulation is reduced, and the ripple factor is also reduced. And if I use with filter, then these all things also be improved. So therefore we will be go for bridge type rectifier rather than the center tap rectifier. So this is nothing but the this is with respect to the observation or result which are done over here. Okay, so okay, thanks for listening the video, and in the next video I'll be explaining you about the introduction about the other three experiments. Okay, okay, thanks for watching. Thank you.